So here's my presentation. Right, so it's on differential topology, and this was inspired by an independent study I've been working on with Professor Wei-Min Chen at UMass. So, what's the motivation? So the study kind of comes up everywhere, in particular the physical sciences. So like in general relativity, manifolds will come up as space-time, and in mechanics they might appear as phase spaces and energy surfaces. There's also more examples like in economics and in chemistry, I believe. I think chemistry is another example of energy surfaces, specifically physical chemistry, but yeah. So they come up everywhere, so they're definitely worth studying. Topological manifolds, and then we're going to kind of restrict the differentiable ones. So in my intuition, I drew a kind of a overly simplistic picture of a pendulum where, here's the, my pen isn't working, but here's the momentum versus position space, and here's the actual physical state space, and when you put enough potential energy into dropping the pendulum, you get different phase spaces. So if you had enough to make a full revolution, your phase space might look like, not closed. It might look like this or something. So this would be the manifold, and then this would be the state space. So an n-dimensional topological manifold is just a second countable Hausdorff space that's locally Euclidean. So the Hausdorff and second countability requirements are kind of technicalities. I'll skip over them for now. The most important one is locally Euclidean. So what that means is that for every open patch on M, so like every open set, you want there to be a homeomorphism from that open set into another open set in Rn. So common spaces that do this is Rn itself, the sphere, the cylinder. Obviously it's a manifold because like every slice is homeomorphic to S1, which is a manifold. Mg, which is the genus G surface. So for example, M1 is the torus, M2 is the 2 torus, and so on. And there's more complicated ones like Calabi-Yau manifolds that appear in algebraic geometry, and if you study like characteristic classes in K-theory. I won't get into that now, but they exist. So what is the differential in differential topology? Well, we can kind of just refine what we mean by locally Euclidean. So what we do know is that if you take an open cover, what you can do is that for each index, you want there to be a homeomorphism into Rn. So if I pair these, phi I and ui, it's going to be called a chart or a coordinate system, and I can put them into a bigger set called an atlas. And furthermore, any two charts are going to have overlap, specifically CR overlap, if the transition map in Euclidean space is a CR map, right? So in the picture, you have UI that projects down, and then UJ projects down by phi j, and then if this is a CR map in the Euclidean sense, like with Jacobians and whatnot, then the charts have CR overlap. That's pretty much it. And if you take a maximal CR atlas, then it's going to be called a CR differential structure on the manifold. So one technicality is the kind of invention of adapted maps. So if you took two manifolds, M and N, I can define a map between them, and furthermore, I want to call it adapted if the image of an open set under F is properly contained in V. And it's sort of a convention so that you can define a new map called a local representation, so that if you take a point in phi of u, so in Euclidean space, I can come up by the pullback, apply F, and because I'm adapted, I land in an open set that is governed by psi, and then I can project down into psi of V. So the picture goes as follows. You're in Euclidean space in phi of u. So I pull back by phi because I'm a homeomorphism, and then because F is properly adapted, I definitely land at V. And then, well, because the N is a manifold, there's a chart V and psi, so I can come down into RK, and so that defines a map here. And then if the transition is differentiable, then we say that F is differentiable between differentiable manifolds. You can also think of the basic equivalence relation called diffeomorphism, which is categorically speaking the isomorphisms in the category of CR manifolds, where your objects are CR manifolds and morphisms are CR maps. You can choose or think of it that way or not, but that's the precise definition of diffeomorphism. And then we can define tangent vectors. So in metrizable spaces like the Sn, for example, well, a tangent vector is just sort of like you can imagine like taking a point and then you have a line or a plane. A plane is more appropriate for a sphere, and then vectors living on the plane that are orthogonal to the sphere at that point are tangent vectors. But we can kind of make this definition a lot better in the case of general manifolds by defining an equivalence relation, where xia is equivalent to yjb if x is identically y, and if a gets sent to b by the following map, which is precisely the derivative of the coordinate change evaluated at the image of little x under phi, which is a homeomorphism. So there's going to be a picture, but basically if you differentiate the coordinate change and evaluate at this, then if you send A to B, then these are equivalent. And of course, this notion makes sense because this is happening between Rn and Rk, for example. Well, actually, it's happening just in Rn. So you only need one Jacobian. All right, and then you can define what's called tangent bundle. It's just a collection of all of your tangent vectors. It's actually it's the set of all of these. So I guess in this example, Tm would be the set of all of these. Furthermore, you can kind of extend by induced maps. Yes, you can extend on induced maps on the homeomorphisms with the same equivalence relations. I won't get into it too much for the sake of time, but the one thing I kind of want to mention is that there's a lot more gaps to fill here, and it gets really interesting because you can sort of recover the intuition of what tangent spaces are from calculus and kind of embed that again into differentiable manifolds. And now, again, this is really only going to work because you have homeomorphisms from open sets on the manifold into Rn. And so the fact that you can kind of recover this, the usual intuition from say, calculus is kind of remarkable. Okay, so I have a little bit on just immersions and embeddings. So let F from M to N be a C1 map. You want to be immersive at a point if the linear map, so tangent space at a point, is injective, and likewise submersive if it's surjective. And then if you get an immersion that maps homeomorphically onto its image, that's of course an embedding. So for example, the projection map is a submersion. The proof is not hard. You can just compute its Jacobian, and you get a block matrix where on the top left you look like identity, and then everywhere else is trivial. And the rank, it doesn't have full ranks. So the rank is precisely the dimension of Rn, which is n, and so you get a surjection, and so at every point. So by definition, this is going to be a subversion. And a little bit more on immersions, I think I would just finish by talking a little bit about a very popular topological space called the Klein bottle. It's kind of an overused example, but one thing to talk about is, like, you might have seen this drawing of a bottle that kind of intersects itself. And I'm here to tell you that's not what a Klein bottle is. This is an immersion of a Klein bottle into 3 space. And you can kind of see it by, well, if you put a cell structure on the Klein bottle, and then I can reproduce a cylinder, there's a way to, my artistic abilities are not that great, but there's a way to kind of pass the top of the cylinder into itself, and then you get an immersion of K. But this is not K, because it's a little, not terribly hard to prove, but you can prove that this does not embed in R3. And the definition of embedding is the one I gave up here, because you can't map homeomorphically into R3. You're going to need at least R4. Right, so that was just some interesting topics that we've covered. There's a lot more I've left out, but hopefully this will give you some good intuition for at least the beginning of the subject. All right, thank you.